method development study. I don't know what a lot of that means, but we're about to find out, and I'm very excited. So please take it away, Ivan. Thank you.
Thank you for that introduction. Good afternoon. My name is Ivan Guzman, and I am proud and excited to present my research, the absorption of complex molecules on SAMs to model crude oil mixtures. And this is going to be particularly a quartz crystal macrobalance method development study. So, as many of us know, crude oil extraction is an ongoing process in which workers retrieve crude oil from these underground reservoirs using techniques called enhanced oil recovery techniques. And these are just ways to simply be able to retrieve the oil more easily. Maybe by adding water or surfactants to the oil, one can make it more mobile, easier to retrieve. And so what happens is workers retrieve this crude oil from the underground reservoirs, and then it's sent to petroleum refineries, where it is further processed and transformed into gasoline for the automobiles that we use, different forms of fuels for different types of transportation, or just overall different forms of energy. And so crude oil itself is consisting of a very complicated matrix. It's not just one simple molecule whenever we obtain it. As we can see from this picture here, it contains tons of different hydrocarbons, some asphaltenes, kerosenes, even some natural gases as well. And so essentially what the research entails is we're using alkene thiol self-assembled monolayers, or SAMs, which are just functionalized surfaces, to be able to elucidate the fundamental mechanisms of how these aliphatic and aromatic species aggregate and clump together. And at the end of the day, we're trying to study the disorder and how these molecules aggregate to not only aid in enhanced oil recovery techniques, but also to minimize the waste whenever these petroleum refineries are studying these oils, because like I said, it's further processed and transformed to all of these different types of energy. And so we want to try and make sure to understand the basic science so petroleum scientists can later be able to study and further use this knowledge to make more sources for energy. And so two of the main techniques that I'll be using, that I use for this research, is called PM-IRAS, which just stands for Polarization Modulated Infrared Reflection Absorption Spectroscopy. And that is a mouthful, but in essence what it is, it's a type of Fourier transform IR that characterizes the vibrational peaks of the molecules that we're studying. And so on the right here, we have our quartz crystal macrobalance, and this is what I'll be particularly discussing today. So in essence, it's a way to quantify the amount of molecules that absorb onto our surface. And so it's very important because this technique is actually very fastidious among scientists. And in this presentation, I'll be able to describe a robust method that I created for an aqueous method, and then kind of show how we're applying it to the research of crude oil that we're trying to do. So quartz crystal macrobalance, what is it? How does it work? This is a very sensitive analytical technique that estimates the mass per unit area by measuring the frequency versus time of a resonating quartz crystal. And so this right here on the bottom right is our resonating quartz crystal. On the bottom is quartz, and on the top we have that gold layer. And so kind of like I said with SAMs, these are functionalized surfaces. So this QCM crystal serves as a great way, as a great substrate to be able to actually attach an alkene thiol and actually study if anything is absorbing onto that layer. And what we see here is whenever we choose like a molecule, for example, sucrose, and it actually absorbs onto the surface, we see if more things absorb, we get larger changes in frequency. From like these three molecules here, we get this drop in change in frequency, but more molecules, we get more of a drop. And the reason why that is because frequency is directly proportional to changes in masses. And that is known based on the Sartre equation, which is this one right here. And this is a very valuable technique because we're able to quantify the amount of these complex molecules that we're trying to study and see how much actually absorbs onto our surface. And kind of like I said, we first need to develop an aqueous method just to make sure it's working with the things that we have in our lab. And so that's kind of where I go into next. So this is the aqueous fluidic configuration. That's just like the way the water moves and stuff. And this is only for water as a solvent. And so what we have here, this is actually what I did throughout most of the summer. We put our sample here, and obviously the solvent being water flows through the use of a peristaltic pump into a bubble trap, aided by a vacuum. And like I said, QCM is a very sensitive technique. So even air or a bubble introduced into the system can actually have very damaging fluctuations in the frequency of our data. So that's obviously something we're trying to minimize whenever we introduce solvents and our sample into the system. And so this is, like I said, for aqueous technique. So we have our bubble-free solvent going into our QCM, which is recorded by a computer, and then out into a waste beaker. So kind of like I said, we first had to develop this aqueous method because obviously for organics, there's a lot of things to take into consideration. And one of the first rules of business is trying to come up with an experiment to see if this method actually works. So that's kind of what I'll be going into next. So it's kind of an experimental outline. So first, I'll kind of go over how I used like a proof of concept experiment using this aqueous method, using bovine serum albumin protein. And next, I'll kind of introduce how we started to introduce like a precursor to like these asphaltene mimics found in crude oil. So naphthalene served as like a precursor molecule to complexity. And then kind of later to finalize everything, I'll say how naphthalene wasn't really the best choice and how we had to switch to another molecule, horny, which is a little bit more complex. As we can see, we go from two rings here to a 6-ring molecule here. So obviously a little bit more complexity in that side. Okay, so whenever we did previous research, we know that bovine serum albumin is a commonly studied protein in SAMs. And the reason for that being is because protein-SAM interaction has been studied for different types of purposes, such as biosensing applications and just overall different types of biotechnology and biosensors. And what we know from previous literature is that this protein is actually, it absorbs dependent on the terminal ends of SAMs. Depending if a SAM is methyl terminated or hydroxyl terminated, obviously the methyl being hydrophobic and the hydroxyl being hydrophilic, we can have different characteristics of BSA absorption onto that SAM. And so kind of what we know from previous literature is that methyl terminated SAMs absorb more BSA than the hydroxyl terminated ones. And this is just kind of one of the things we wanted to prove with IR and then complement with QCM. And so kind of what I did here is I created two different types of SAMs, a methyl terminated SAM, which is the DDT, and the hydroxyl terminated SAM, which is that MUD. And clearly from what we can see here, these ami bands are indicative of BSA absorption going on in the first place. And what we see is that we actually have a higher intensity for that ami2 band, for that DDT, than for the MUD, which does suggest that yes, there was more BSA absorption onto our methyl terminated SAM than that hydroxyl terminated SAM. And so this is really great news. Like, we already knew this from previous literature, but we want to know if it shows complementary results to our QCM method that I developed. So that's kind of what I'm going to next. So this is the QCM data for a very similar experiment that I performed. And so what's going on here is first, we added solvents, just DI water, for the baseline to stabilize, and then we introduced our BSA. And as we can see, for that DDT methyl terminated group, we actually see a larger change in frequency before it stabilizes. And for that MUD, it's way less frequency change than that DDT. And this does suggest kind of how I was saying, how changes in frequency are directly proportional to changes in masses. A larger drop in frequency does suggest more BSA absorption on that SAM. And further, we can quantify that once again using the Sabry equation, and we actually indeed see that 946 nanograms of BSA absorption on that DDT compared to the 612 nanograms for that MUD. And so this is great because obviously we're trying to incorporate this into organic species for the next project, but making sure that it works for an aqueous solvent first is the perfect example of how to move on. So that's kind of the next thing, right? We're trying to move on, try and study these aliphatic and aromatic species. And we have to obviously switch for organic solvents if that's the case. And so whenever we're switching from aqueous to organic solvents, there's a lot of troubleshooting that needs to be going on here, right? So obviously there are a lot of things that are chemically incompatible, such as the bubble trap, the vacuum, and the tubing. All of those three things had to be removed. We had to switch the tubing to a more chemically compatible, resistant tubing. And obviously there are a lot of benefits, but a lot of disadvantages as well, because as we know with QCM, it's very sensitive. And so an air bubble present, like I said, can disturb the fluctuations in frequency of our data. And so one of the things that we tried to try and minimize this, because we don't have the bubble trap or the vacuum anymore, we decided to sparge our solvent. So sparge in a solvent means introducing an inert gas like nitrogen to displace oxygen and just trying to get rid of any other gases that might be present in our solvent. And so this is kind of just showing what I'm doing right here. And after that, obviously, we're trying to non-incorporate air. So we have our solvent, but then the main question is how are we going to move from introducing our solvent to our solute plus the solvent, right? And so that's kind of our next question that we're trying to consider. But one of the molecules that we first need to try and start using just the solvent, just run it through the QCM, seeing how the data looks. And so kind of one of the first molecules that we chose as like a precursor to asphaltene is the naphthalene, which is this one right here, and it's soluble in pentane. And so for like this next slide, I'll try and characterize it using the IR, FTIR, and we'll try and see if we can actually see those naphthalene peaks. And so there's a lot going on here, but let's break it down. So what I did is I created a methyl terminated SAM, which is that ODT right here. And that's indicative of these 4 methylene backbone peaks that we see that the SAM is present. But we also took an ATR scan, and the ATR scan is just a way to make sure where the naphthalene peaks would be in this region of the IR data. And so we see from this peak, naphthalene peak should be present right here. And what I did is I created 2 millimolar naphthalene solution, and then just added drops, successive drops, onto our gold piece here. And what we can see is, even after adding successive drops, we see no changes in every single one of these. Like, this one is the same as this one, and so on. We see no naphthalene-associated peaks in this region of the IR. And then on the right graph, it's just a different region, wave number region of the IR spectrum. We see also here these peaks should be associated with naphthalene present, but we actually see no peaks associated with naphthalene. So obviously this is a concern because there isn't any naphthalene that is bulk on top of our SAM. And one of the things we were thinking, why this isn't happening, is because naphthalene is a very low molecular weight molecule, but it also has a very high vapor pressure. So obviously it's very probable that whenever we add naphthalene into our gold piece, we actually, whenever we're trying to transfer to the sample holder, the naphthalene actually evaporates before we even take the scan. So obviously there's a very huge problem, and one of the ways to mitigate this, or to minimize this, would be to introduce a little bit more of a heavier molecule with a lower vapor pressure. And that's kind of exactly what we did, moving on with chlorine. And so chlorine here, it's a very similar project experiment with what I did. I created a 1 millimolar chlorine solution, and because this is actually a heavier molecule and a much lower vapor pressure, we actually do see that we see the bulk of chlorine that adheres onto the gold. And I say bulk and not physisorbed because on the gold, whenever we have our gold piece, chlorine can absorb onto the surface, but then more chlorine could actually absorb on top of more chlorine, and just kind of different orientations going on. So physisorption means whenever it's just a single and even layer of just chlorine molecules on top of the gold. But here, this is just showing how we were able to successfully add in bulk chlorine, just a lot of it on top of that gold, so fully saturated, if you will. And so this is very important because obviously chlorine is a little bit more complex than naphthalene, and now the next question would be to try and incorporate this IR data, but with our QCM. And we know chlorine is there because, once again, based on an ATR scan that we had previously taken, we see these like sharp peaks that are associated with chlorine, so we know it is definitely present in bulk. And kind of moving on here, this was one of the most recent experiments that I did, and it's actually a very successful indication that the baseline for running organic solvents through the QCM is fairly stable. As we can see, from 0 to like around 550 seconds, the relative baseline of that is very stable. And one of the ways to check if the frequency actually changed a lot was to introduce air into the sample, just to make sure to see how much of that frequency was going to change. And we can clearly see, just by adding air into the system, we see that huge rise in frequency. And so that's obviously something we want to mitigate for the future. But now this is currently, as we're running solvents through the system, the next step, kind of like I said, was now introduce our sample, benzene. And I chose benzene because it's very soluble. Chlorine is very soluble in benzene. And so the next step would be to not just run benzene through the QCM system, but actually the solutes plus the solvents. And so in this case, chlorine plus benzene. That's kind of like where we're at for the next step, trying to incorporate a more, I guess you could say, more robust method, not only for aqueous, but now switching for this organic species and trying to actually quantify, it's like, kind of like I did with the BSA protein, but actually quantify how much chlorine is absorbing onto our surface. And with that being said, I just want to thank the American Chemical Society Petroleum Research Fund for funding this project. And thank you to my research advisor, Dr. Thompson. She's been wonderful in my journey here at St. Edward's. And without further ado, I'll open the room for questions and really appreciate it. Yeah.
I wanted to ask, what made you pick naphthalene as your solvent in the first place?
Naphthalene as like the molecule, the precursor. So naphthalene it's safe to work with, relatively cheap, and it's something that we just had there, right? So it's obviously in crude oil, there's a ton of like aliphatic and aromatic, even some simple molecules as well, just simple alkanes in there. But naphthalene is just one of those molecules that we got stored in our cabinet, and it's a very, I mean, if you take a look at its structure, it's very, you could say very similar to some of the molecules that are present in crude oil. Like, I mean, it has some rings in it, so it just has a very similar structure. So that's a precursor to a bunch of these more complicated things. Yeah.
So you talked about using the volatility of your solvent system.
Right.
I was wondering if you had ever thought about potentially like combining solvents at certain percentages, so both an aqueous solvent and an organic solvent, in order to both get be able to work with your aromatic species, but also stay not as volatile.
Yeah. So we haven't thought about combining two solvents of different like organics versus an aqueous solvent. However, I feel like that because the system is like it's a lot of chemical incompatibility with our tubing and a bunch of like the bubble trap and vacuum. I don't think that could work because obviously there's still some organic solvent there. It's probably going to degrade the tubing over time, or it might have an impact on like the bubble trap. So maybe that could work, but using like the same tubing perhaps. So.
Once you get the system working where you can use organic solvents with things in them, what will be some of the implications?
Yeah. So obviously, once we get this working, we can actually quantify like how much of an organic species is like absorbing onto a surface. That's obviously has great implications because we know how much is there. And kind of like I originally said in like my first big picture slide, we're trying to like elucidate the mechanisms of like disorder and aggregation of like these complex, very big aromatic species. And so this is like a basic science. So like understanding how much is absorbing and like how it's absorbing is very crucial for like petroleum scientists later on to be able to, you know, not only help aid and enhance oil recovery techniques, but just making sure how to further like process this crude oil, being able to like separate it and actually like using it for its different purposes, so like fuels and all that stuff.
Very, very good job. Thank
No,
you.
thank you.
So you set the stand for another minute. Gonna introduce. We're not done yet. This is Dr. Rebecca Thompson, who worked with Yvonne and is going to say a few words and also present him with a cord and stole that he'll wear at graduation to recognize all of his amazing work in the honors program, including but not limited to this amazing project. Thank you so much, Dr. Thompson.
Yeah, so I am very excited to present both Yvonne and Omar with their honors cords because they are two students that I've known since they were first years. They were in my general chemistry class, and I quickly recruited them to do research with me because I saw how bright and excited they were, and they've both done a wonderful job. Yvonne in particular has been really tenacious on this project. This is an instrument that we've had for 5 years and not really used because it's hard and tricky for all the reasons he discussed. And he's been really persistent on this project, working hard, putting in all the time for running and classwork and working on the QCM and troubleshooting it week to week with me. And so I am really excited that we're here, and I know you're headed for a very impressive career.
Thank you.
Yeah. Thank you.